Now let's look at some examples of hypothesis testing with proportions. Let's start in the textbook with number 18. So First USA is planning a new offer for its cardholders. They'll give double airline miles if you go online and register for the offer. So to test the effectiveness, they sent out offers to a random sample of 50,000 cardholders. Of those, 1184 registered. Staff member suspects the success rate for the full campaign will be comparable to the standard 2% rate used to see in similar campaigns. What do we predict? All right, so the first thing that we want to do is we want to write down what our hypotheses are. So for us, notice that we think that it's going to be like the standard 2% rate. So that would be our null hypothesis. So let's get a pen, and there we go. So the null hypothesis, H subscript 0, colon, population proportion P equals the 0.02 would be my 2% rate. Now, we don't have any reason to believe that our offer is going to do better or worse. So the alternative hypothesis has got to be two-tailed. It's got to be P does not equal 0.02, since we don't have a direction to conjecture. So those are our hypotheses. Now, what are the assumptions and conditions for inference? So remember, our assumptions and conditions when we're dealing with proportions, first thing we need is randomization. And it says this was a random sample of 50,000 cardholders. So we are definitely okay there. So the random condition was met by the random sample. And now the next thing that we need is that 50,000 is less than 10% of all cardholders. Well, notice that if I multiply by 10, I'd get 500,000. We're told it's 2 million cardholders. So our 10% condition is met. Since 50,000 is less than 10% of 2 million. Okay, and then our third condition is to make sure that we're going to have at least 10 successes and 10 failures. Well, I immediately know that's met because we got back 1184, and so 50,000 minus 1184 is our failures, 1184 is the successes, that's bigger than 10, we're good there. But we're going to do it off of what we predicted with the 2%. So we're going to calculate 0.02 times 50,000 as our number of successes. And we would get, what, about 1,000? It doesn't matter, that's bigger than 10. And now check our failures. Well, we would do that, the failures is the opposite amount, right? So if 0.02 is how many successes we expect, then 0.98 times 50,000 failures we expect. And that would be 49,000. And that's bigger than 10. So all of our conditions are met for inference. We can go ahead and proceed. So we want to answer the question, do you think the rate would change if it uses this fundraising campaign? To answer that question, we are going to do a hypothesis test. Now, in doing a hypothesis test, I can do it on my calculator or I can do it out by hand. So I'm going to show you first how to do it out by hand. Notice our number of successes here is that 1184 is how many we got back. So that's the X in our little formula. And so our N is the 50,000 that we sent out to. And so we would construct the p hat as being 1184 out of 50,000. This is the X over N for the p hat. So that works out to be 0.02368. All right, now the next thing that we need is our standard deviation for the sampling distribution. Standard deviation of p hat. And if you remember, that's going to be the p times q over n. Well, remember, our p up here is 0.02, so that's going to be 0.02 times 1 minus 0.02 over the n of 50,000. and then square root all of that result, and we'll get 0.000626. And now the z-score can be calculated by doing our sample proportion, 0.02368, minus the population proportion that we assumed, 0.02, over our standard deviation, 0.000626. And that z-score ends up being 5.88. Now, 5.88 is very large. That's definitely going to be bigger than 10, so I'm pretty sure that we're going to have a probability that's less than alpha. But to find that probability, I'd use my calculator or the chart. If I'm using the chart, look up the z-score of 5.88. If I'm using the calculator, you go normal CDF, 0.02368, comma, 1, comma, 0.02 to point, and then 0.000626. Okay, my lower bound, upper bound, I could have put like a million there, but one's big enough when I'm dealing with these small numbers. Here's where the mean is settled and the standard deviation. Okay, so lower bound, upper bound, mean, standard deviation. And that gives me back, looks like about 2 times 10 to the negative 9th. So that would be 8 zeros. And then a 2. But now, remember, this is two-tailed. Right up here, two-tailed. Because it's a does not equal. We have, whoops. Because it's a does not equal, we have a value over here and over here. But this that we calculated down here is just the value to the right. So to get the other value as well, I would multiply this times 2, and that would be my p-value. It's going to be 0.08 zeros and then a 4. Okay? Now, let's see how to get that on the calculator. So on the calculator, what I'm going to do is I'm going to go to Stat, and then over to Tests, and we're running a 1 proportion z-test, option 5. My p-naught was 0.02. My x is the 1184, and my n is the 50,000. And then it's a does not equal for the alternative hypothesis. And let's go ahead and calculate it. Whoops. Skipped right over my screen. Okay. And so notice that right here you see that z-score that we got, 5.88, and that probability, 8 zeros, and then a 417. Same probability we found by hand, okay? So what do we think? Because this probability is so low, our decision here, so we go right over here and would say decision, we're going to reject the null hypothesis since our probability p was less than alpha. Okay, what does rejecting the null hypothesis mean? We don't believe that's true. So, in fact, ours was bigger, so we have evidence, our conclusion then, we have evidence to believe more than 2% will register. let's look at number 20 in this same section here. And this time we're not going to do it by hand. We'll just use our calculator. So for number 20, according to the Association of American Medical Colleges, only 46% of medical school applicants were admitted to a medical school in 2011. Upon hearing this, the trustees of Striving College expressed concern that only 77 of the 180 students in their class who applied to medical school were admitted. Now, the college president assured them that this is just year-to-year fluctuations. We want to know, is it right that they're concerned? Okay, now, what are our hypotheses? My null hypothesis here if I can get my pen to write. Okay, let's just do it like this. My null hypothesis is that, all right, 46% is the standard, so the population proportion should equal 0.46 at our school as well. Now, my alternative hypothesis, notice it said here that the Board of Trustees is concerned that only, in other words, they think it's too low. So we were trying to test the hypothesis is P less than 0.46. All right, let's check our conditions. So here are my conditions. Is it random selected? Well, no, it's not randomly selected, but that is typical of the class year. So I don't need the random selection because I'm using that as one class out of many classes that are randomly selected. So we're okay on that. Now, is our 180 less than 10% of all medical students? Yep, I'm pretty sure that that's going to be the case. There's more than 1,800 medical students admitted to the college. And then 10 successes and failures. Well, we've got 77 successes and 180 minus 77, so they're both bigger than 10, but we should check them against the 0.46 that is assumed to be the case. So for my last part of checking the conditions, I would do 0.46 times 180, and I'm going to get a number bigger than 10, and then I'd do 1 minus 0.46, so that would be 0.54 times 180, and I'm also going to get a number bigger than 10. So all the conditions are met. We can go ahead and find the p-value. So we're going to hit stat, go over to the tests, again option 5, and this time our p-naught is 0.46, and our x is we admitted 77 out of the 180, but this time we're doing a one-tailed, we think it's less than 0.46, so we want to hit enter on that. And then we're going to go down and we're going to calculate. And our p-value is 0.193. Now, is that less than the alpha? Well, if the alpha is not specified, and it isn't in a lot of problems, then we just need to see an alpha that's reasonable. The alpha value of 0.05 corresponds to that 95% being in the middle, which we know is about 2 standard deviations. Remember before we were classifying anything as 2 or more standard deviations as being a bit unusual. So I'm going to default to alpha being 0.05 whenever I don't have it specified. So 0.19 is bigger than 0.05, so I would fail to reject. What does that mean? I can't say this is wrong. So we do not have evidence. We do not have evidence that less than 46% are admitted on average across all the years. Okay, this just happened to be a weird year. All right, so should they be concerned? No, they should not be concerned because that is just normal year-to-year variation. Or at least we have no reason to believe that it's not just normal year-to-year